Because we only have two dimensions represented on our piece of paper by default, by looking at the actual lengths and distances represented on the page, we can only really discern the physical length or measurement of things that sit perpendicular to the angle in which we're looking. Meaning, if we've got a box that is aligned such that we're looking straight on at one of its faces, we can judge its height and width, but we have no way of judging its depth. Foreshortening arms us with the tools to help the viewer understand the other lengths, of which some components exist in the depth of the scene. To put it simply, a piece of paper can only give us so much direct information. We use foreshortening to help provide extra info so the viewer's brain can better and more completely understand what it's looking at. The primary manifestation of foreshortening is something you're probably familiar with to some extent. As things get farther away from us, they appear smaller. They are of course not actually physically getting any smaller, but they appear that way to our eyes. Another manifestation of foreshortening is the degree shift that we talked about in regards to the ellipse section of this lesson. Where given a cylinder, the farther end will appear wider than the end closer to the viewer. This actually applies to all forms, even boxes, where the far end will appear proportionally wider. That said, in this video, we're primarily going to focus on the shift in scale, the tendency for things to get smaller as they move farther away. So if you're unsure of what the degree shift is, I recommend that you visit the ellipses video after watching this one. I'll include a link in the description, but since you're at this video, I do expect you've watched it already. Now, our gut instinct here is to think about this scale shift as it applies to whole objects. This student, for example, is getting farther from us, and so it's getting smaller. It's applying to the entirety of the student. Eventually, he'll get so far away and so small to our perception that he'll collapse into nothing but the tiniest little speck, which eventually our eyes will no longer be able to see. We refer to this, the point that is infinitely far away from us, as a vanishing point, one of the building blocks of technical plotted perspective. We can also think about this in terms of distances between sets of objects. If we clone our student and have all of them run away from us, the distances between them shrink, just as the students themselves do. But the student is a complicated object, made up of tons of smaller forms, and a lot of stress-induced illnesses. We can think of him as though he's made up of a series of dots, and as he moves farther away from us, the distance between those dots shrinks. Instead of thinking about foreshortening as though it impacts entire objects at once, we can think about how it applies to space in general. The spaces between the parts of a single object and the space between different objects in the scene. Let's set aside our complicated student and go back to talking about the problem in a much simpler form by looking at boxes once again. Like our student, a box is made up of a series of points, or vertices, all connected to one another by edges in 3D space. The box simply allows us to see this in a much simpler state, while still demonstrating all three dimensions of space. Each box features three sets of edges, a set that goes across the width dimension, one that goes across the height dimension, and one that goes across the depth. If you look at the box from an angle like this, it might not be entirely clear which corresponds to the width and which corresponds to the depth, but honestly, it doesn't really matter that much, as we're just labeling them for the sake of explanation. Each set contains 4 edges, all of whom are parallel to one another in 3D space. This is where terminology becomes important, so I'm going to try my best to be consistent. When I'm talking about 3D space, I'm going to refer to them as edges. When I'm talking about their projection onto a flat, 2-dimensional page, I'm going to describe them as lines. Because we're talking about how to draw 3-dimensional objects, we are going to be constantly jumping back and forth between talking about the 3D space we're trying to represent and the 2D space in which we're representing it. As each of these edges extend farther back in 3D space, moving away from the viewer, the distances between the lines that represent them on the page get smaller, until finally they converge to a single point. That point, which we identified earlier, is the vanishing point for this set of edges. The vanishing points for edges that run parallel to the ground plane will be situated on the horizon line. Although you can certainly have vanishing points that aren't on the horizon, it just means that the edges it governs are not parallel to the flat ground like these vertical height edges. Keep this in mind. As a set of edges rotates in 3D space, the vanishing point that they converge to will move around. We do not control this vanishing point directly, but it is their orientation in 3 dimensions that allows us to identify the correct location for the edge's vanishing point. It's worth calling out the fact that as those edges rotate, the vanishing point will not move at a consistent rate along the horizon line. This can actually get kind of confusing, so don't worry too much about it if it doesn't make sense right away, but the further out to either side of your image, and even beyond it, your vanishing point goes, the more it's actually going to move for every degree the edges rotate. This is something we'll look at a bit more closely in the next video.